In the previous lecture, we have talked about the analytic inverse kinematics. Compared to the previous lecture, we will talk about the numerical inverse kinematics IK problems. The iterative numerical method can be applied if the IK equations do not admit analytic solution. Actually, the 6th degree of freedom robotic manipulator does not have any least center. Actually, we don't have any analytic solution. In this case, the numerical iterative method can be applied to the kinematic problem to solve the IK. So numerical IK issue is very important for the general robotic kinematic problems. Okay, even in case where the analytic solutions does not exist, the numerical method are often used to improve the accuracy of the solution. So I think the numerical IK issue is more general compared to the analytic IK. Okay, there exists a variety of iterative methods for finding the roots of a nonlinear equation because the kinematic issue is all the time nonlinear. And our aim is to develop ways in which to transform the IK equation so that they become amenable to existing numerical method. Okay, so as a representative method for iterative numerical method, okay, Newton-Raphson will be used in this issue. Okay. In many cases, we seek the closest approximate solution. In the case of the redundant manipulator, because redundant manipulators has the many IK solution for a given specific task posture. So at the time, we will apply the optimization to determine the one solution to minimize the optimization issue. Like this, we can determine how to solve the IK issue for the redundant manipulator system. Okay, we seek a solution that is optimal with respect to some criterion. So it depends on the criterion. Criterion is different. At the time, we have a different posture of the robot. Okay, briefly, I will explain the Newton-Raphson method. Maybe you have learned it in the numerical analysis class. Okay. Okay, to solve the equation g theta setting as a 0 numerically for given differential equation. Okay, this equation, differentiable equation, g is mapped from Rn space to the Rn space. Assume that the initial guess theta 0 will be applied to the solution as a starting point of iterative method. Okay. In order to apply the Newton-Raphson method, Taylor expansion will be used. Okay, G is nonlinear equation, so we will expand it at the set 0 initial guess, and then we will truncate it at the first order. Okay. Let's write down the Taylor expansion at set 0 initial guess. So we will initial guess will be applied to get the numerical value of the G, and then round G round theta will be the matrix, and then theta minus theta 0. Maybe the higher order term will be the second order, and then twice differentiation will be required to write down the higher order term, Anyway, we will remove, we will neglect, we will ignore these terms. Okay. Round G, round zeta transpose. Okay. As mentioned before, this will be the some matrix R n times n. Okay, G, every vector will be aligned according to the column vector. Okay, so G has the n-dimensional element as a column vector, G1 through Gn. Okay, and then the first element should be differentiated with respect to the row direction. So zeta transpose is required, like this. The first element G1 will be differentiated at the beginning zeta 1 to the last zeta n. So we have n-dimensional row vector, okay? And then second term will have the same form. And the last element of the G vector, Gn, should be differentiated with respect to the row direction from the zeta 1 to the zeta n. Like this, we can obtain matrix keeping only the terms up to the first order, okay, neglecting the higher order terms. Okay. On the other hand, the g zeta is assumed to be the 0. So this term is the 0. So if we obtained this one from this equation, then okay, then we have this equation. Okay, is it right? Minus G0, and the inverse matrix is applied to both sides, and then zeta 0 will be added to both sides. So we have this equation. Okay, using this value of the zeta as a new guess, every time the result will be applied again, here and here and here. Then we can make an iteration using this equation. Okay, so this new value, the new guess for the solution, repeating the above, we get the following iterative equation. Okay, from the initial guess, we should define some criterion to stop. So maybe the zeta k plus 1 minus zeta k, the absolute value of this one, maybe the relative value will be required. It should be some very small value denoted by the epsilon. Like this, we can determine some criterion to stop. Okay, above iteration is repeated until some stopping criterion is satisfied. Okay, this kind of Newton-Raphson method to find out the IK solution of the robot manipulators. Okay, numerical IK algorithm of a robot system. For the Newton-Raphson method, let's define XD, the final posture of the robot, and then the pose kinematics. Okay, zeta d will be the target value for given xd, the end effector posture. That's the problem of IK. So let's denote g zeta d as a xd minus f zeta d. Okay, for given initial guess zeta 0, we will assume that zeta 0 is very near or close to the target value. Okay, that's the assumption. The difference is very big between both. We cannot assure this iteration is converged to some value. So we need to add some assumption. Initial guess is near to the final value. The kinematics can be expressed. Okay, here, this kinematics can be expressed using the Taylor expansion. So the first numerical value and the first order differentiation and the first error between the set target minus initial guess. Okay, as mentioned before, this is the matrix. Actually, this is Jacobian. Evaluates at the initial guess. Then we have the approximate iterative solution. Okay, this is the target. So xt minus fx initial value, and the inverse matrix is applied. So the plus denotes the pseudo inverse of the Jacobian, and by adding both sides at the 0, like this we can write down the iterative method for numerical IK. It can be generalized like this. Okay, this method is very effective. So according as k goes to infinity, iterative time is going to infinity. At that time, the solution theta k will approach to the target value. Okay, now we have shown the pseudo inverse, so we should learn the pseudo inverse property in detail. So this page shows the specific property of the pseudo inverse. Actually, the pseudo inverse is called as Moore-Penrose pseudo inverse because the Moore and Penrose are defined the pseudo inverse concept. Okay, in general case, pseudo inverse is denoted by the J plus. Okay, it means generalized inverse. Consider the equation Z is equal to Jy. Y belongs to Rn space. Z belongs to n-dimensional Rm space. We should consider three categories. The first one, J is square and per. J has the same row and the same column. The J inverse is obtained by using the many kinds of method, but the effective method is the LU decomposition. LU decomposition is very computationally efficient, so if you can choose the inverse method, the LU decomposition is recommended to reduce the computational time. Anyway, LU decomposition can be used to determine the inverse matrix. On the other hand, J is pet. It means very pet. The rectangular matrix is given as a J. N is larger than the M. Okay. We will add another assumption. J is full length. In this case, the J pseudo inverse should be obtained as a tall. Is it right? So J pseudo should be identity as a small size. Okay, but J pseudo J will be composed of 1 or 0 matrix as a big size, but it is not equal to identity matrix. So in the case of pet J like this, the pseudo inverse is defined J transpose JJT inverse. Many cases it is called as right inverse because J J store must be identity matrix. Actually, the light store, the physical meaning of the light inverse, it minimized to norm. That's the physical meaning of a light store inverse. Okay, let's assume that the y, the to norm is will be minimized, subject to the equality constraint z as a jy. Okay, it is called as a constraint optimization. Okay, the solution will be the light store inverse. Okay, let's derive. In order to solve the optimization problem, the Hamiltonian matrix is defined, the optimization value and constraint. Optimization value must be the constant, must be a scalar value, but the constraint is the vector. So we need to row vector to connect between both. So the Lagrange multiplier will be introduced to connect the measure at the performance index and the constraint. Okay, let's write down this one. Rewrite. Okay, H is given by y transpose y, lambda transpose z, lambda transpose jy. All terms are scalar. Okay. Here, let's take the differentiation with respect to y. So the first term has a 2y, but it is scaled with the 1/2. So we have two terms. First, differentiate this one with 1/2y appear. It appears two times, so y. It is not dependent on the y, so it will be the 0. Okay, let's take the differentiation with respect to y here. The column vector cannot be differentiated with the column vector, so we take the transpose y transpose j transpose lambda. It will be differentiated y. Actually, this is not dependent on the y, so this one will be the identity matrix. So we have the j transpose lambda here. Okay. As you know, the constraint that is equal to jy, but here y is equal to j transpose lambda. So j transpose lambda is applied to here as a minimum value, as an optimum value of the Hamiltonian. And from this equation, we can calculate lambda because the JJ transpose is the small size square matrix. Okay, so if lambda is obtained by taking an inverse JJT. Okay, this lambda will be applied to the minimum value of the Hamiltonian. So here, this is the lambda. So we arrive at the definition of J store, light inverse. So light store inverse, this one, minimum solution of 2 norm of y. Okay. Okay. I think you should memorize this concept. The pet J, the long matrix in the horizontal direction. The inverse will be the tall, the long in the vertical direction. At the time that this tall inverse matrix is called as light inverse. Light inverse is the minimum solution of the 2 norm. Okay, 2 norm minimum solution. In the case of the pet J, then solution is the smallest joint variable change that exactly satisfies equation this one. Okay. In the case of the redundant manipulator, this two-norm minimum solution is used. So if you are using the pseudo-inverse solution in manipulating, in controlling the redundant manipulator, the smallest motion will be obtained from the pseudo-inverse. Okay? Because light pseudo-inverse is obtained from the minimum of two norm. Okay? So motion two norm will be minimized in the case of the light pseudo-inverse. On the other hand, J is the thin or tall. J is the very tall matrix, but it is full length. In this case, the pseudo-inverse is a little bit different from the light pseudo. Okay, in this case, J pseudo-inverse will be the pad. So JT, J inverse, J transpose, it is called as left pseudo-inverse. Actually, the left pseudo-inverse minimize the error to norm, this one. Okay, so let's prove the previous, the aforementioned concept. Let's take the Hamiltonian. The error is given by like this. Okay, it will be expanded 1/2 J transpose Z minus okay, the Y transpose J transpose Z will appear 2 times, so 1/2 cancel out each other, and 1/2 Y transpose J transpose J Y. Okay. Okay, let's take the differentiation with respect to Y. Okay, so first term will be the minus J transpose Z. The second term, by this one will be differentiated. The remaining one will be this one. This term will appear 2 times, so 1/2 cancel out. So we have this one. Okay, the minimum is achieved at the zero. So we will have some relationship between Z and Y. Okay, so it is a square. So if we apply the square matrix both sides, then Y will be denoted by this matrix. Okay, this one is defined as a left pseudo-inverse, but the notation is the same, J pseudo. So we have this equation. Okay, the J is very tall. In the case, the left pseudo-inverse will give you the error minimum solutions. Okay, if n is smaller than m, solution may not exactly satisfy this equation, but it satisfies the condition as closely as possible in the least square sense. Okay, let's memorize 2 pseudo-inverse. Right pseudo-inverse is the 2-norm minimum solution. Left pseudo-inverse, least square solution. Okay, that's the conclusion of this page. Okay, let's apply the Newton-Raphson method to numerical IK. Okay, for given posture of end-effector frame, and then the initial guess should be assigned as a near value to the final target value, and the set iteration number as a 0, and then error is defined. This is the given target. Theta is the initial guess, and then the error is larger than some threshold value. At the time, we will apply Newton-Raphson method to find out the next value, and then we will increase I. This value will be used as a new guess. This iterated to satisfy this condition, small or error is smaller than the epsilon, then this iteration will be stopped. Okay, the final target is given by the posture of the ND effector. At the time, we have the very simple numerical IK, but the error, in our case, error is not given by the difference to homogeneous transform. Those are not equal to each other. Is it right? We have derived the TSD belonging to the SE3 using the 16 number. So the error should be defined as a new form. So we will use the body twist instead of error. Okay, so to begin with the body twist, let's obtain the TBD. Okay, if the final, okay, this is the body frame. Robot is given like this, and the effector is here. The body frame is attached like this. Here, this posture is the final target. Let's assume that this is the final target, TSD. I will assign the TSD. This configuration should be moved to here. Okay? At that time, we will write down the TBD, body to the desired. Okay? This TBD is obtained, the T inverse SBD and the TSD. T is specified by the user as a target. TBD is obtained using the POE, is it right? So the inverse will be applied to obtain the 2TPS. 2PS time TSD will be equal to the TBD. And then let's take the matrix logarithm. Then we have matrix form of body twist from the TBD. Okay, maybe the VB matrix form is the omega B cross product form and the VB and the 0, 0, 0 and the 0. So the result will be this form. From this matrix, we can extract the omega B and the VB as a 6-dimensional form. So we can get the body twist. Okay, this kind of concept will lead to the following IK algorithm, analogous to the previous page coordinate vector algorithm. Okay, the user provides the TSD belonging to the SE3 form, and the initial guess is given. At the time, matrix logarithm will provide body twist. Okay, so and then the body twist will be applied to here. And then the omega B and the VB is smaller than, larger than the threshold. This procedure will be iterated until the error epsilon, the omega B and the VB is smaller than the specified threshold. Okay, example 6.1. It's not difficult. The initial posture is given by like this. This is the initial. The target will be given by this posture. We should solve the IK using the numerical algorithm. That's the problem of example 6.1. Now we apply the body Jacobian Newton-Raphson IK algorithm to the two robot. Each link has the 1 meter in length. We would like to find the joint angle that places the tip of the robot. Okay, here. Okay, it corresponds to the 30 and the 90 degree for each joint. Okay, using this data, we can determine the TSD, the final position and orientation. Okay, TSD is given. Here we can write down the TSB as a function of the theta. Maybe the initial TSB can be calculated. Okay, maybe E2 S1. E2 M E2 P1 theta 1 E2 P2 theta 2 as a body form POE. Okay, the M is very easy because the space at the 0 position, this is the B frame, this is the S frame, and if we apply the theta 1, omega 1 as a unit magnitude, maybe it will move like this. This is 1 meter and 1 meter, so 2 in y direction. So 2 will appear here. And this omega 2 as a 1 will be applied, then we have the y direction as a 1 unit, like this. And the final position will be the 2, 0, 0. So the position is like this. The initial and the final frame aligned each other at the same form. Okay. From the body twist, we can apply the Newton-Raphson method. Okay. The first step, the initial angle 0 and 30. Okay, the target, the alpha value is obtained like this. At that time, the body twist is given from the logarithm of the body twist. Okay, logarithm of POE of TPS and TPD. And at that time, the omega and the VB is very big. After the first step, we have the big difference, and then x, y, and y, and the point, and the body twist is calculated using the TPS, TPD. At the time, the omega b and the VB is a little bit large. We will apply the one more. Then it approaches to the final value very fast. The end point and this very small omega and v is obtained. Anyway, it is big compared to the threshold, so we will apply the one more. At that time, we have the exact value, the exact inverse kinematic solution. Just after 3 steps, the body twist as a given, body twist is given as a 0 vector. So the omega b and VB will be 0. Like this, just the 3 steps will provide very exact solution of the IK problem. Like this, the Newton-Raphson method is very computationally efficient. Okay, Newton-Raphson method is good tool to calculate IK, inverse kinematics of the robot kinematics. but I'd like to recommend you to use the inverse velocity kinematics compared to the numerical or analytical method. Okay, till now we have talked about the computation level. We will take the time derivative to the ik. Then we will arrive at the velocity level. Velocity level mapping, the velocity level mapping requires the Jacobian between the theta dot and the x dot. Okay, those kind of mapping will be treated as a linear mapping. So this kind of linear mapping is very useful to provide good solution in the level of the velocity. And then we will take the integration to obtain the computation. Okay, so let's summarize. For given POE, let's take a time derivative. Then we will get the Jacobian mapping. In there, we will solve inverse kinematic problem at the level of the velocity, and then we will take the integration to obtain the theta. Those procedures will be better. Okay, so let me explain. One solution for controlling the robot so that it follows the desired end effector trajectory, TSD. Okay, TSD is given as just one point that is called as a set point regulation, but TSD is given by as a function of t. We should follow some end effector frame, the varying end effector frame. Okay, in this case, we can calculate the theta d. Okay, if we know the theta d already, theta d is given. This is the desired, not actual. By using some sensor such as the encoder or potentiometer, then we can obtain the angle of each joint will be applied to here. Then desired minus actual value is subtract each other. Then we divide time difference between both, and then we can calculate theta dot. This kind of theta dot can be applied to the velocity controller. It will be explained in the chapter 11, maybe 11, I'm not sure. At the time, we will deal with in detail theta dot can be used for the controller. So this amount to feedback control, because desired new joint value are being compared with the most recently measured actual value, this one, in order to calculate required joint velocity. Okay, this is not actual. This is required joint velocity to this value approach to here. Okay. Okay. On the other hand, another option, we will use the Jacobian mapping theta dot J pseudo body twist or desired twist. Okay, if we want to use the J body JB or JS, you can choose either this one or this one. It depends on this one or this one. Is it right? Maybe you know how to obtain this matrix. So for given TSD, if we take the time derivative, this one or this one, then we can write down the JB or JS, body Jacobian or space Jacobian. It will be applied to here. Then we can get the theta dot. This theta dot should be integrated to obtain the theta. So for given theta dot, theta can be obtained. The previous, the previous theta plus theta dot current k and the delta t will be multiplied to obtain new theta k from the previous theta. Like this, after calculating theta dot, theta can be obtained. So we can complete the IK issue. Okay, from now we will talk about many optimization methods. This topic is a little different from the textbook. Anyway, I think you should understand how to obtain the Steinbergs, wave Steinbergs, inertial wave Steinbergs. Those kind of things will show so their own property. So I'd like to recommend you to understand the concept of Steinbergs. Okay, the use of Steinberg's J pseudo returns the joint velocity theta minimizing what? 2 norm. So 2 norm means will be equal to theta transpose theta as a square root value. The minimum of this one will be equal to minimum of theta transpose theta. Is it right? The minimum of this one will be equal each other. So we will take the 1/2 theta transpose theta with the equality constraint twist equation, okay, Jacobian mapping. So our first step is to write down the Hamiltonian, okay, minimize value and the constraint. Constraint is vector, so Lagrange multiplier should be applied to connect the scalar to the column vector. Okay, so second step is the differentiation. Round h round theta dot will be equal to equal to theta dot will appear 2 times, so 1/2 will be cancelled out. And here, okay, lambda transpose J theta dot, okay, round theta dot. The column vector cannot be differentiated with the column vector. So we will take the transpose operation. Theta dot transpose J transpose lambda round theta dot. Because this is a scalar, the 3 transpose will be equal to 3. So this kind of concept is applied to here. Here, round theta dot transpose round theta dot will be identity. The remaining term, J transpose lambda. So minus J transpose lambda appears here. So we have theta dot is equal to J transpose lambda. Okay, this equation will be applied to constraint equation. So we have this one. JJT, this matrix is square. So inverse is applied to both sides. So we have the lambda. Okay, lambda. Lambda will be applied to the minimum solutions. So we have this one. The J store will provide the 2 norm minimum solution. Actually, we have treated again. Okay, the new issue, inertia weight Steinbergs. Okay, inertia appears both between the theta dot terms. So it must be the kinetic energy. Okay. Let's minimize the kinetic energy subject to constraint the same. Okay. Maybe the Hamiltonian matrix will be given by the scalar term plus the constraint column vector. The low Lagrange multiplier vector will be required to make the scalar value. Okay, let's write down again 1/2 theta dot inertial matrix theta dot lambda transpose twist minus lambda transpose j theta dot. Okay. Let's take the differentiation with respect to theta dot. So these terms will appear 1 over 2 m theta dot 2 times. So m theta dot. This is not dependent on the theta dot, so it does not have any impact on the theta dot. Okay, here, let's take the transpose operation. Theta dot transpose j transpose lambda. So this term will be differentiated with respect to theta dot. The remaining terms minus j transpose lambda here. Okay, from the constraint, theta dot will be applied. Here is theta dot m inverse j transpose lambda. Okay, this theta dot will be applied to here. So we have this equation. From here, the lambda can be calculated using the inverse of the previous term. So this one. This lambda will be applied to here. Okay, so lambda will be replaced with this term, and we have this very big, very long equation. Okay, I will denote this matrix J M pseudo. Okay, as you can see here, J is applied to both sides. In front term, we have the same matrix, so it will be the identity. So it is the lightest inverse. This is the lightest inverse. Okay, let's memorize M inverse J transpose J M inverse J transpose inverse. Okay, it's the J inertial waist inverse. Inertial waist inverse minimize the kinetic energy. Okay. Okay, let's inverse to be more general. Okay, let's find joint velocity theta dot minimize the kinetic energy plus rate of change potential energy. Okay, many cases, if you know the notation of the robot system, this term will be the G transpose as a function of theta. Sometimes, in order to apply the obstacle avoidance, it can be used as a spring-like equation, spring-like potential energy. Anyway, any kind of potential energy given, the rate of change will be applied to the minimized performance index. Okay, so H is the gravitational potential energy at the time, or the artificial potential function can be used here as a H. Okay, let's take the time derivative. As mentioned before, this term is the gradient of the H, and this term is the theta dot. So it can be used as a scalar value. So we will apply it to here. Okay. We will solve the IK, satisfying the Jacobian relation here. Okay. The Hamiltonian matrix is given. Round H, round theta. Okay. The first term is this one. Second term is the K from here. Take the transpose operation, theta dot transpose, gradient H, round theta dot. It is identity matrix, so delta H is given, okay, without transpose. We have the we have shown it already previous page. So it is equal to J transpose lambda. Okay, from here, theta dot will be the M inverse J transpose lambda minus gradient H. Okay, this term is applied to here, so we have this equation. Okay, actually we have two terms, this one and this one. Okay, so in here we can obtain lambda. Okay, J M inverse J lambda is equal to twist plus J M inverse gradient H by moving to here, and then taking an inverse, we have the lambda like this. Okay, this lambda will be applied to here. Lambda will be applied to here. Okay, so theta dot is given by like this. Lambda will be applied to here. Then we have three terms. It's very long. It's difficult to understand it. Okay, so let's introduce inertial waist inverse. Okay, it must be what? Inertial waist. Okay, one more. How about this one? Inertial waist. Is it right? So this terms inertial waist and J M inverse gradient H as M inverse gradient H. So by adding these terms, I minus J inertial waist J M inverse minus gradient H. So we have this equation. Okay. It is spanned on the inverse of range space of the inverse. But how about this term? This is the orthogonal to each other. So it spans in the range null space of the J, minimized on these terms. Okay, let's interpret the inertial waist inverse. As mentioned before, inertial waist as to this form. Okay, in here's Lagrange multiplier value, and theta dot is given by like this from the previous slide. Okay, actually the Lagrange multiplier value can be interpreted as a range in the task space. Okay, so this is similar with the range. Okay, actually the Lagrange multiplier has the two terms, the first one and the second one. So the first term can be interpreted as a dynamic force generating the end effector velocity. So in order to produce end effector velocity, Vd, the first term will be used to generate. Second term can be interpreted as a static range counteracting the gravity or obstacle avoiding potential field. Okay, you have 6.3, 4, 5, 6, 8, 10, 11. I'm sorry, this is the 6.15. And not many, but problem is not easy. So you should prepare for this homework number 5 on chapter 6. The due date is the May 10. Upload it or email me, including the PDF file. Next week, I'm sorry, not next week. It is Thursday. Thursday morning, 9:30. We will have some discussion or exercise time. So anyway, I will prepare for some exercise problem. But if you want to solve it together, you can email me or you can email or Kato